Okay, I think we can get started. Very happy to have Beata speaking on the embeddability of the unions. Sorry about the very short introduction. Please go ahead.
Thank you very much. So yes, I want to speak about the following problem. So imagine that we have a metric space and that this metric space is a union of two, essentially, disjoint sets. And both of those sets with the metric inherited from the whole metric space embed into a given Banach space or a given metric space. A problem is, does this imply that the union itself also embeds into that same metric space or class of metric spaces with the distortion that doesn't depend on the spaces, but just on the distortions of embeddings of the two pieces? So let me remind the definition that everybody, I think, remembers, but I will use, we say that the metric space embeds into another metric space with distortion D if there exists a function phi such that the distance between the images is bounded below and above by constant times the distance between the original points. So, so this problem has been studied by Mendel and Naor in 2013 and answered positively in the case when X is a class of ultrametric spaces, right? Ultrametric spaces, as everybody remembers, are those spaces that satisfy a stronger version of triangle inequality, which is recalled over here. So they showed that if A and B embed into some ultrametric spaces, then there exists another, possibly another ultrametric space so that the M also embeds into that other ultrametric space. And then another question of the same sort was considered by Makarichev and Makarichev in 2016 in case when X is a Hilbert space. So again, they proved that the answer is yes in that case. They gave an estimate for the distortion of the union, which is written over here. And their method of proof was actually very ingenious. And it was relying on the classical theorem of Kirsch-Brown, an extension theorem that every Lipschitz map from a subset of L2 into L2 can be extended to a Lipschitz map from the whole space. So they did not perform the extensions of the original maps, right? Because we have those two subsets. Each of them have embedding into a Hilbert space. They did not do the extension of one of these embeddings, but they did a very clever construction doing certain nets, and I am not going to go into detail of this, but it relied in a very essential way on using the Kirsch-Brown extension theorem. So such theorem is not available outside of Hilbert space. So the people asked, various people ask questions, well, how about if X is L1, which is an important space for computer scientists and for us, and how about LP for P other than 2, other than infinity, of course. Will this be still true? So, so let me maybe reveal the punchline. I do not know the answer, even at the end of this talk, if the answer is true or not. However, there was a certain possible counterexample suggested, and that's what I want to talk about. So let me start from recalling a definition of spaces of negative type. So the metric space is called of negative type. If M with the square root of the metric embeds isometrically into L2. And it is a classical result that spaces which embed isometrically into L1 imply that they are of negative type. And if we try to use the result of Makarichev and Makarichev, imagine that I have two spaces which embed into L1. Well, then of course, their snowflakes, the 1/2 snowflakes, will embed isometrically into L2. Therefore, by the result of Makarichev and Makarichev, their union with this snowflake metric will embed bi-Lipschitzly, not necessarily isometrically. You remember that estimate was not isometric, into L2. Well, so one could think, okay, so this is a very good start. Can we then conclude that this union with the original metric, not the square root, embed into L1? Well, unfortunately, there is an example which was kind of constructed. I don't believe they were thinking about this problem I am discussing, but Lee and Moharami in 2010 constructed an example of a metric space which is bi-Lipschitz equivalent to a space of negative type, like this A union B square root of D embeds bi-Lipschitzly, meaning we will have this situation. However, this space M cannot be embedded into any space of negative type, in particular into L1. It cannot be embedded with bounded distortion. The distortion depends on N in an essential way. So this is kind of showing some delicate nature of the examples that that exist. So there is no immediate conclusion over here. I mean, of course, the example of Lee and Moharami is not satisfying this extra condition of being a union of two negative type spaces. However, it does show some difficulty that arises. So let me mention a few more words about spaces of negative type. So in 1990s, Goemans and Lignon asked whether every space of negative type embeds into L1 with constant distortion. So this question was answered negatively in 2005 by Kot and Vishnoi, who showed that there exists an example of an endpoint metric space, which is of negative type, such that every embedding of X into L1 requires distortion at least of this order, right? Log n to the power 1/13. And moreover, in their example, they had that in addition, every not overly large subset of the space X does embed isometrically into L1. So this was kind of a surprise, I believe, when this was discovered. Since then, there was quite a bit of work trying to improve here this bound, the log to the power 1/13. And the most recent example that I am aware of is the result by Naor and Yang from 2018, which shows that any embedding of the Heisenberg group H5 into L1 requires distortion at least of the order square root of log n. And this is relevant because earlier, Lee and Naor showed that this Heisenberg group H5 has an equivalent metric which is of negative type. So this improves this 1/13, this log n 1/13 quite a bit over here. So let me say very clearly that it is an open question if we have a metric space which is of negative type and which is a union of two subsets which are embeddable into L1, which does not have to be the case. But if it is the case, does that imply that M embed into L1? I do not know the answer to this question. Right, this is a much...
Can I ask you a question, Beata, please?
Sure.
This Randrianantoanina result, what is N in this statement? This is the embedding of the Heisenberg group, which is a given object into L1, which has a norm or distortion, rather at least square root of log n. What is the little n?
They are talking here about discrete Heisenberg groups.
Okay.
Not just about Z. Those are discrete finite Heisenberg groups.
Okay, so that would be over Zn probably.
Over
Z
Zn.
divided by
Yes.
Nz. Okay.
Over Zn.
Very good. Thank you, Beata. Thank you.
Yes. Yes, I should have over Zn. Okay, so as I said, maybe I am not having the style for, making good movies. The final answer here is I don't know. So let me go back and try to think of possible counterexamples for the problems. Can we construct a space which consists of two pieces, both of which embed well into L1, and so that the union possibly doesn't? Right, so the question that arises, okay, so what spaces do we know that embed well into L1? And this is a very general kind of question. And one of the important results is this one. Mendel and Naor in 2015 showed that if you take any real number, any positive real number, and if you consider L1 with the truncated metric, meaning the distance, which depends on lambda, is minimum of that number lambda that is arbitrary but fixed, and the L1 distance. And if you consider it with this truncated metric, then L1 embeds into L1. And this, I don't know how important this looks on the first sight, but it is a very important question, a very important statement. And in particular, it allows people, it allowed Mendel and Naor to apply the theory of Brudny and Krugliak, who studied concave functions and who proved that every concave function can be equivalently presented as a sum of these kind of metrics. So the conclusion is that if we take any concave, non-decreasing continuous function, omega, which is positive for all positive values of t, and we consider L1 with the metric which is that concave function of the L1 norm. For example, power 1/2 is one of such functions, but it can be any concave function, that this will embed into L1 with constant distortion. The distortion is not going to be 1 necessarily, like it is with if omega is just power 1/2, but it will be constant distortion. I think the distortion is E divided by E minus 1, if I remember correctly. Actually, the distortion is less than 10, not E divided. So this is, this gives us a big class of examples of metrics that embed well into L1. And here is a small digression. if we ask the same question, not in L1, but in LP, so earlier, Mendel and Naur also proved that this is the same exact statements, both of them, are valid also in L2. It is not true when P is bigger than 2, and it is open and explicitly asked by Mendel and Naur in 2015 whether this remains true for P between 1 and 2. So I don't believe that answer is known. So a twisted hypercube construction, right? This is something that appeared in the title of the talk. Let me try to explain what I mean by that. So I will consider a Hamming cube, just the 0, 1 to power n. I will consider alpha, which is a number strictly bigger than 1/2 and smaller or equal than 1. And I will consider r, which is a constant. That constant may depend on n. N is fixed. And we consider 2 copies of this Hamming cube. And we consider these 2 copies, and we consider them as a graph. And we consider, so here, and if I want to go from 1 copy of a cube to the second one, I only can go vertically, right? So those are all the edges, and we put the weights. So we put the weight, which is this is an example designed for a specific purpose that I will describe in a moment. So the weights are the following. We take the power 1/2 to the alpha, we take the L1 norm divided by this constant, and we take here the fixed R. And we consider the shortest path metric. So this is the original construction called twisted hypercube. It was used by Johnson, Lindenstrauss, and Schechmann in 1986 to prove that there are no uniform bounds on extensions of alpha Helder maps into Hilbert spaces, right? Where alpha is any one of those numbers between 1/2 and 1. So what they proved is that if you have an identity map from the zero copy of the Hamming cube, that map cannot be extended with small bounds, right? So you obtain that the L will necessarily be bigger than n to this power. In particular, when alpha is 1, meaning our function f is Lipschitz, then we have here L, which is greater than 4th root of n, meaning you don't have the Lipschitz extension property. Right, so related examples were used by Lindenstrauss. This is maybe like the original construction in '64, by Kalinescu, Karloff, and Rabani in 2005, by Lange, by Naur and Rabani. And in 2015 and 17, Naur and Rabani asked whether this specific metric space possibly is a counterexample to the union problem. And I don't know, this may go back to Johnson, Lindenstrauss, Schechmann, this specific suggestion for a counterexample. So I want to look at this twisted hypercube construction one more time. So as it is easy to compute, the distance between the points is equivalent to the following thing. So this is the weight on the 0 copy of the cube. Here you take the minimum of the 2 weights, and here is R, that parameter R, plus the minimum, right? So those are kind of very ugly formulas. I want to go away from those formulas. I will start using my notation using the concave function. So omega 0 every time I will use the symbol omega, it will denote the non-decreasing concave continuous function. So we have this omega 0, we have the omega 1, which is a different function, and we have here r plus omega 1. So this is the general form of this metric in the hypercube, without going into the detail of what exact formulas are. What is important here is the second inequality, that omega 1 and omega 0 are related in this way, that constant r satisfies this inequality, that omega 0 is less than omega 1 plus 2r, less or equal. All right, so let me now go and do the general definition of a twisted union of metric spaces, which is the definition that follows the ideas of Naur and Rabbani suggested in their paper in 2017. So we start with any metric space, which has two metrics on it, D0 and D1. And then we also have a function from M to 0 infinity, which satisfies such two conditions. I am going to discuss those conditions in a moment. They are very natural. On the next slide, I will show why they are natural. So we have those two technical conditions, and then we take two copies of our metric space, and on every edge which is in the 0 copy, we put distance 0. In the 1 copy, we put distance 1. And the edge connecting the two copies from x0 to x1, we put this r of x. So this is more general than the previous one because we allow it to be a function. And we call this a twisted union of those metric spaces MD0 and MD1. So this notation kind of doesn't include the function r of x, but of course the function r of x is hidden in there. So what are those conditions? Well, those conditions is like I have here, I have my x0 and x1 and y0 and y1, right? So here we put the distance r of x, here we put the distance r of y, here is the d0, and here is d1 of xy, right? So now if I want to look at the distance from x0 to y0, that should be smaller or equal than the sum of those three things that I just shaded, which means this, right? And then if I want a distance from x0 to x1, if I want it to be truly r of x, then it should be smaller than the sum of those three edges. So those two conditions, this one and this one, they are precisely the necessary and sufficient conditions so that the weights that were stated are equal to the weighted graph distance. So I don't need to adjust so that's why they are very natural, and I will always make an assumption that they are satisfied. All right, so the metric itself is defined in this way, that the distance between points in 0 copy are d0, distance in the 1 copy are d1, and the distance of the edge connecting is r of x. So then how much is the general distance from x0 to y1? Well, so we cannot compute it in general, but we can compute it in certain situations. We can compute it if we make an assumption that R of X is constant, and of course, R of X always satisfies those two conditions. Even if I forget to say it, I mean it. So if that is the case, then the distance from x0 to y1, so I am going to use this symbol here. This symbol represents, it means that this is small or equal than constant, one constant times this quantity, and it is greater equal than a different constant times the same quantity. This is the meaning of this yellow symbol. So, so it is equivalent to this quantity, minimum of the two metrics plus R. And if R of X is not constant, but if there exists another constant so that one of the metrics is majorized by the other one, then we also can give a formula for the general distance. And again, here again, this symbol with the subscript C0 means that this constant that's supposed to exist may depend on the value of C0, right? Otherwise, they were absolute constants. So if we have one of those two assumptions, then we have the equivalent formula for the entire metric. And we have two theorems. So the first theorem is that if we have a metric space with two metrics, and if both of those metrics embed into L1 with some specific distortions, and imagine that we have also a constant K and a map such that the minimum of the two metrics is equivalent, embeds into L1, right? M with that minimum of the two metrics embeds into L1 by Lipschitz. And moreover, our twisted union is done with a constant, right? We just have those two conditions reduced to just this one condition to which is written here. And then the twisted union of MD0 and MD1 embeds with a distortion which is bounded by a constant which only depends on the original distortions and on this constant K here. So in particular, as a corollary from it, we obtain that a very general twisted union or very general version of that original example of Johnson, Linder, Strauss, and Schechmann, if we have any subset of L1 and we have any two concave functions, and then we take the twisted union of omega 0 of normal 1 and omega 1 of normal 1 with constant R, which this constant R certainly has to satisfy this condition. Then no matter what they were, it will always embed with a distortion which is bounded by an absolute constant. I think that on the last count, that constant, I think, was less than 114. I am not going to go into the computation why this much, but so this answers that question that this is not a counterexample. This is a very general situation. However, the condition here, though, is that this is constant weight between the two copies of the metric space. So one can, so here I am writing M rather than hypercube. One can, of course, think of kind of, iterating this procedure, right? If I take the hypercube like the original hypercube and then take a twisted union of it with a different hypercube, this theorem 1 is fairly general. It will allow producing larger and larger copies of such metric spaces, which still embed into L1. So the second theorem kind of looks very technical. Let me state it since it is here. So again, I have two metric spaces that embed into L1. And I imagine that this condition, by the way, is satisfied by the metrics in the original hypercube example, that one metric is dominated by the other metric. And then imagine in addition that there exists such a difference of metrics. And that the minimum of this difference and the metric Rx plus R of Y, I do know this is becoming kind of technical, but I apologize for that. Imagine that that embeds into L1 with some constant distortion. And if all these conditions are satisfied together with our standard conditions over here, that we always make an assumption, then this metric embeds into L1 with some distortion, which is bounded on depending only on all these constants and not on the metric itself, metrics themselves. So in particular, if R of X is a constant function, then here for this D2, one could simply take D0, because certainly this first inequality will be satisfied, I mean, trivially really. And this one, if R of X is constant, then the minimum of a given metric which embeds into L1 and a constant also embeds into L1, which I am going to show you in a moment. So if that situation happens, then this works. But in a case, this is our best attempt at a general result, allowing arbitrary weights between the cubes. So I do want to say a few words about the proof. The proof is very different from the proof that was used for the case of Hilbert spaces by Makarychev and Makarychev, who, as I said, they used Kirsch-Brown extension theorem of Lipschitz maps. Here we don't have it, we don't use it. And the original proof was a very careful matching of specific embeddings, but right now it actually is a very simple proof. Let me try to, so I'm trying to prove theorem 1. All right, so I have those two, I have this metric space with two metrics, D0 and D1, and I have R, which is a constant. So the first thing I will do is I will define a new metric called rho I, which is the minimum of the given metric and the constant 2R. Something like was in the theorem of Mendel and Naur about truncation of L1 metric. So we know that the truncation of L1 metric embeds into L1, and then this is the exact constant, exact distortion that they obtained. And we also know that our metrics DI were embeddable into L1. So if we consider composition of those two maps, the Mendel-Naur map and our embedding of DI, we of course obtain that this is bounded above by the product of those distortions times the minimum of the two metrics. And it is greater equal again times the product of those two constants, which are both 1. So we obtain an embedding of this M with this metric rho I into L1 with the distortion slightly bigger than the original. So now we define a metric D2, which is simply the minimum of the two metrics, which were given to us on M. So, and recall that rho I was defined in this fashion. So what we observe very easily is that if we take rho I plus D2, those two, then we have this inequalities. Well, the upper inequality is of course obvious because this is a minimum of those two. So it is smaller or equal than di, and this one is also smaller or equal than di. So the sum is clearly smaller than 2 times di. Now, greater equal, right? I think I wrote it here. The greater equal, well, it's a minimum of those two things, right? So if the minimum of one of them is di, well, then it's bigger than di. The sum will be bigger than di. So what if the minimum is not di in either of them, meaning the minimum of these two is 2r, and the minimum of these two is the other one, right? But this is exactly the inequality that I said we always have, that guarantees that the weight of every edge is equal to the distance between edges. So we obtain this in every situation. All right, so now this is the end of the technical part of the proof. We just fix any element from our metric space M, and we define the embedding as follows. So phi 0 will be the embedding with the norm rho 1, rho 0. Phi 1 is the embedding with the metric rho 1. Psi is the embedding with the metric D2, the minimum of D0 and D1, and R is our parameter. So we define the embedding of the twisted union in this way. And it is a very quick check that this works, right? Because phi 0 is an embedding of rho 0. This is a constant. This is an embedding of D2. And this is also a constant, 0. So we obtain that this is rho 0 plus D2, which is precisely what we said, that this is equivalent to D0. So our embedding works correctly on the 0 copy. Identically, it works correctly on the 1 copy, because then this part is 0 and this part is equivalent to rho 1, and everything else goes the same. So how about for the mixed copy? Well, so then we have phi 0 of x minus phi 0 of m0, which is rho 0 from x to m0. Then we have rho 1 from y to m0. And then we have the minimum of d1 and d0. And then we have r. So rho 0, remember, is a minimum between 2r and d0, right? So this thing is smaller or equal than 2r. I mean, constant times 2r. And so is this one. So in general, it's smaller or equal than d2 plus some constant times r, which is equivalent to this, which is equivalent to the distance between x0 and y1. And the greater equal, well, those rho 0 and rho 1 are certainly greater equal than 0. So the greater equal is even simpler. So we obtain that this is a bi-Lipschitz embedding. And this is the end of the proof, which is kind of amazingly simple. And relies in a very essential way on the embedding of truncations. All right. So I guess this is all that I wanted to say about this. Let me let me remind you that we did not prove, we do not have an example which is a counterexample. We still don't know if that kind of example exists or it doesn't exist. The last few minutes, I wanted to mention a lower bound on distortion, right? Because one could ask, if I have A and B embedded isometrically, could I possibly conclude that A union B also will embed isometrically into L1? So Makarychev and Makarychev showed that this would not be the case in case of L2, and they showed an example, a family of examples for every epsilon, implying that the distortion will have to be at least 3. I mean, 3 minus epsilon for arbitrary epsilon. So what I want to do here in the last couple of minutes is show, in a sense, a much simpler example with that same lower bound for required distortion. So let me remind you the definition of stable spaces. And so the space is called stable if whenever we have two bounded sequences in our space and we take the limits in different orders, right? Then the limit doesn't depend on the order in which the limit is taken. So if that happens, the space is called stable. Otherwise, it's not. So Krivine and Moret in 81, they showed that Hilbert space and all LP spaces are stable, right? Those are classical results. And what we want to consider is we want to consider...
Beata.
Yes.
I have to mention that L infinity is not stable.
L infinity, yes, that is a typo. I am so sorry. I did not mean to write that. I did mean to write smaller. Sorry about this. It's one of those typos. Right, so what I want to consider is I want to consider the following construction. If I take two copies, so I have here two copies of natural numbers. Here is one of them, and here is the second one of them. And then we are going to consider the reunion, and we will consider edges on them. And the edge will go from one of the copies, element from one of the copies, to every point which has higher, right? So this one will connect here and there, but not there. Right, so those are all the edges that are there. So in particular, it's very easy to see that if I am trying to see a distance between any 2 points in one of the copies, well, it goes to, goes like this. The distance is always 2 between any 2 points in one copy of N, same in the second one, right? So you can go this way. However, if I take the limits in the different order, if I take the limit as this one goes to infinity and this one is fixed, the distances between I and j is 1. However, if I take the in the opposite order, the distance is 3, right? Because I cannot go back, right? So what we obtain is that we have those 2 copies of N. Each of them is an equilateral set of distances 2 between every 2 points in the copy. So such copies, of course, embed into L1, they embed into every LP. However, the union is not stable because those two limits are different. So since L1 and LP are stable, that means that the distortion of embedding the union has to be at least 3. And which proves that lower bound for the distortion embedding not only into L2, but in any stable metric space. What I wanted to maybe finish saying, I'm not going to go through the proof of it, that one could think, well, can one improve on this constant 3 over there? And the answer is no. The constant 3, which is a very simple application of triangle inequality, that using the trick of stable examples, the highest that one can get over there is 3. So that was the short proof, which I'm not going to show right now. Thank you very much.
Well, thank you, Beata. Okay, questions?
Well, I may have 2 questions, Beata. First of all, thank you for this nice lecture. But then one example, which is possibly trivial, you will tell me, is if you take in your situation A and B be 2 identical metric spaces, 2 isometric metric spaces, and then if you consider the condition you mentioned about the connecting function R for building up a metric space, a metric graph with this function R, you exactly mean R to be to Lipschitz for the distance on A or B. Okay, this is the condition you gave connecting the distance with the function mean that it needs to be to Lipschitz. My question is it possible to make easier computations in this case, maybe playing with this function R that on which you have some freedom? Have you been trying this class?
So you want this function R of X to be non-constant?
Yes, yes. What I mean is that if D0 is equal to D1 and A is equal to B,
right,
you simply need R to be to Lipschitz, and then your conditions are valid. So it gives you maybe some freedom playing with this parameter. And I was wondering.
I would imagine that it will simplify the computation. I don't recall doing this computation exactly, but yes, I would imagine that it will simplify the computation. And I do imagine this will go through easily. But I don't have the computation in my mind right now.
Of course. No, the hope would be, I'm not sure it's making sense, but the hope would be that you have some freedom with R, and then possibly you could construct examples. I mean, that's
you mean, do I expect that if R of X is special, then this union will not embed?
I don't know. I was only wondering whether the class could be used in this context. I know nothing more. I mean,
maybe I will try to check it more carefully, but I don't think this will produce a counterexample. I don't think one could take a twisted union of a space with itself, a special twisted union, so that it will not embed. I would imagine, but maybe I shouldn't say too much. I better check. But I somehow don't anticipate that it will not embed. I anticipate it will embed if that R of X is at least certainly if it is good enough. But if it, but I think it will You see, I am afraid to say the word always, but it is, I would imagine it would embed.
Okay. Another quick question, if I may, since you mentioned Krivine-Moret and the stable metric spaces at the end.
Yes.
Well, you certainly remember that their original motivation was for Banach spaces, and they were able to show that stable Banach spaces contain copy of little LP spaces for specific values of P.
Yes.
What I don't know, because this was before Odell and Schumprecht and solution to the distortion problem, I don't think at the time of their work, I don't think they had good copies of LP. That is, I don't think they were able to show, and please correct me if I'm wrong, I don't think they were able to show that a stable Banach space contains 1 plus epsilon copy of LP.
I think they did. Yeah.
Benjamin, maybe somebody knows?
I think that's what they showed, right?
Yeah, I think so too. I think they showed that.
Isometric copy of those. Yeah, they showed.
Okay.
Yeah.
Then it means that my memory is faulty. It's much better to check it just immediately. Okay, so that was essentially my question, but oh yes, you're right. You're right. They showed it. What was not clear was for infinity norms, but you are absolutely right. Okay, so end of the question, which is not a question. Thank you.
Okay, any other questions?
Just like to say, as someone who works in interpolation theory, the Brudny-Kruglak results were very exciting and interesting for us. And it's very pleasant to see them having a role elsewhere. I see that neither Brudny or Kruglak are listening here, but I will inform them, and I'm sure they'll enjoy watching the recording.
Yes, I think this is a very essential part of this theory, and it was an amazing application here that Mendel and Naur brought.
And of course, thank you very much for a very lovely and impressive talk, Beata. Good to see you again. We haven't seen each other for a while.
Thank you very much.
I remember your kind hospitality.
Thank you very much. Very nice to see you.